Tim Maudlin, welcome to the Uncertainty Podcast.
Thanks for having me.
Of course, I appreciate you coming on. I wanted to talk to you today, first of all, about the fairly small and understandable topic of quantum mechanics. I like to start general and then winnow down. And so my first question is, what is the difference between quantum mechanics and classical mechanics? Because it's my understanding that even Einstein's theories of relativity are instances of classical mechanics. So even those don't represent a break from the classical framework, and yet quantum theory does. So what is the key difference between a classical and quantum mechanics?
That's a good question. I mean, it's often misunderstood. Many people think the key break is something like that there's indeterminism in the theory, or some uncertainty relations, and you can't really find stuff out beyond a certain limit. But what Schrödinger said in 1935, actually in the very paper in which he introduced the cat thought experiment, was that the one thing that forced in quantum mechanics, that forced a departure from classical lines of thought, that's pretty much a quote, was entanglement. And he introduced the German word we now translate as entanglement, in that paper. And entanglement is a situation where, in a kind of obvious sense, if you have two laboratories that are very, very, very far apart, in all classical physics, including in general relativity, the theory could describe the situation in one lab using some vocabulary, and the situation in the other lab using the same vocabulary. And all you could say about the two of them taken together was that. You say, that's what's happening in Alice's lab, that's what's happening in Bob's lab, end of story. And entanglement is a situation where it isn't the end of the story. There's just no way to even describe physically the situation that pertains to both labs together by individually describing each one on its own. And those features that can't be handled that way are entangled features. Now, you don't always have that. I mean, you could set up Bob's lab and Alice's lab in a way that pretty much it would be okay. That's what we call a product state of two systems, where each system sort of has its own little quantum situation. But generally, things get entangled. And when you have two systems that are entangled, you just can't completely describe them by describing them one at a time. You have to take them together. You have to somehow treat them globally as part of a single thing. The way we do that is with a thing called the wave function, which I'm sure everybody's a little bit familiar that in quantum theory, there's a wave function. And the main thing about the wave functions is it just can't be thought of as a local thing. It's somehow a global thing. So I would say if you want to really see what happens in quantum theory that cannot happen in classical theory, look to entanglement. The main thing one of the main things you get out of entanglement is it is exactly the entangled systems that can violate Bell's inequality. And what that tells you is that no classical theory, including general relativity, Maxwell's theory, Newton's theories, they couldn't violate Bell's inequality for experiments done far away. And quantum theory predicts those violations show up. So I think that's
so. Let me ask you.
Yeah,
that's a good answer. One instance of entanglement that I'm familiar with is measuring the spin of a fundamental particle, such that if two of these particles are entangled and you move them to opposite ends of the Earth, if you measure the spin on one, in some sense, you automatically determine what the spin is on the other particle, or you can know what spin someone else on the opposite side of the Earth will measure for that particle. Is that, in a rough sense, an
special case? It's not every case.
Okay.
That's in certain what are called maximally entangled states. Okay. In that case, I mean, you send a particle to Alice, a particle to Bob, and you've prepared them in a certain way. And the best Alice can do, the best anybody can do, they're going to do two measurements of spin, and those measurements will either have outcomes spin up or spin down. The best she can do to predict what she's going to get is to say it's a 50-50 shot. I just, you can prepare, given that what she's going to measure, what Bob's going to measure, you can prepare a state. She has no clue. If you do this over and over again, she'll just get up and down 50% of the time with no pattern. Bob will get up and down 50% of the time with no pattern. But then if you put her results smack next to Bob's, you'll notice that whenever she got up, he got down. And whenever she got down, he got up. Now you can prepare that. That was the kind of situation Einstein was talking about. So in that case, once she sees her result, which she couldn't have predicted, she can accurately predict Bob's. Now, often that's not true. Often what happens is when she sees her result, she can now make a better guess about Bob's, right? She can make a better guess than 50-50, but maybe she doesn't know what it'll be. That phenomenon alone is not spooky. That phenomenon alone is easy to explain without entanglement. That was Einstein's point. So that kind of phenomenon Einstein talked about in his paper, the EPR paper. And what he complained there was that in quantum mechanics, the best you can do is make these probabilistic predictions on both sides. And he said, look, that can't be what's going on. It must be that at the source, it's already determined that, say, Alice will get up and Bob will get down. That's the only way to explain this, that somehow it was already predetermined. But then the predictions shouldn't be probabilistic. The predictions of a complete theory should actually say for each pair, oh, this is going to happen to Alice and that's going to happen to Bob. That could explain the whole thing without anything spooky. That's where we were in 1935. What Bell does later, John Bell in 1963, is say the kind of theory Einstein wanted can't work for the total range of predictions that quantum mechanics makes. So you can't have what's called a local theory that will give you all the quantum mechanical predictions. Now, it's interesting that Schrödinger, even in 1935, just looked at the situation and thought, no, something very, very non-classical is going on here that classical physics, of no kind of classical physics, can account for. Einstein thought he could be clever and figure out a way to do it. And Schrödinger sort of saw, no, what's going on here is too far from classical physics to ever be treated by classical physics. And it turns out that Schrödinger was right, although you sort of need to get to Bell to have the absolute proof of it.
So what is Bell's inequality and how does quantum mechanics violate it? I mean, I know that ties into entanglement, but I'm not connecting the dots.
Yeah, you don't have to even know about entanglement. The nice thing about Bell's work is he just says, look, suppose you have this situation. Alice is in one lab, Bob is in another lab very, very far away, so far that when he does an experiment, there's not even time for a light to get from him to Alice so that can influence her experiment. So just set up that situation, right? And give them choices about the experiments they do. So they can make these choices any way they want. They can make them randomly. They can throw dice. They can, use random number generators, whatever you like. They're just kind of randomly picking between usually two experimental situations. And suppose you have a local theory, which just means that what happens in Alice's lab is determined just by the state of the particle that went into Alice's lab and her equipment. What happens in Bob's lab is just determined by the state of the particle that went into Bob's lab and his equipment. Nothing Alice does has any influence on Bob. Nothing Bob does has any influence on Alice. Okay, so that's a very intuitive way of saying what the Bell locality condition is. And what Bell shows is that for any local theory, any one you want, I don't care whether it's quantum, what you've thought up, whatever you've imagined, any local theory, there are limits to the kinds of correlations that you'll see between what happens in those two labs. And those limits are expressed by something called Bell's inequality. So what Bell says is, look, if you've got a local physics of any kind, the observed statistics can't violate this inequality. But quantum mechanics predicts it'll be violated, and in fact, it is violated. That's the logic. So you're done. You can't have a local theory.
So is that the same issue that this kind of maximal entanglement seems to indicate of faster than light signaling? Or
it's faster than light causation.
Is it the same issue?
You have to be a little careful here. Bell's locality condition is a causal condition. It says all the causes of an event have to lie in or on its past light cone. Causation and signaling are different. I mean, this is absolutely central to understand what's going on. The violations of Bell's inequality says there has to be faster than light causation. Question: can I somehow use that to send signals faster than light? It doesn't follow you can. It doesn't follow you can't. It doesn't follow you can. So if you can kind of cook up theories where, yeah, they're non-local in Bell's sense, but still you somehow can't use that non-locality to send signals. Now, my personal belief is that you can. You just have to be really clever. I mean, and there are schemes for doing so that people are developing, and some theory, a lot of theory behind it. Nothing in a lab yet. But my feeling is violations of Bell's inequality tell us there is superluminal causation. And it would be strange if you couldn't somehow, if you were real clever, turn that into superluminal signaling, right? I mean, maybe you can't. Maybe there's some master principle of some sort that says, okay, the causation is there, but you can't signal with it. But to me, that sounds kind of weird and conspiratorial and implausible, right? And in fact, and there are people working on this, I could give you their names. If you look in the literature for various schemes people have for explaining certain data, they all actually end up implying you could superluminally signal in different ways. I mean, the schemes are all different, but it's just technically really, really, really hard to avoid it. And my guess is you don't avoid it. My guess is it's there, but you have to know, you have to have a theory to know how to look for it.
So then the big question I'll ask you is that Albert Einstein was quite famous for saying that nothing can travel faster than the speed of light. So how does this implication of quantum theory and this experimental result cohere with that claim? Does it refute?
It doesn't. It shows Einstein was wrong. It contradicts.
Okay.
Period. End of story. That's why he didn't, but he didn't like quantum theory because he saw from the beginning in 1926, right at the beginning, Einstein looked at quantum theory as it was being developed. And he said, wait, this has spooky action at a distance. This has what he called telepathy, which was this non-locality.
Yep.
And he said, I don't like that. People think he didn't like the indeterminism, but that isn't what he really didn't like. What he really didn't like was the telepathy, was the spooky action at a distance. And what Bell was interested in was exactly, is there any way to avoid it and keep the same predictions? And what he proved is that the answer is no. Now, his proof came, a few years after Einstein died. So Einstein didn't know about it. I like to think if he read Bell, it's an easy proof. If he read Bell and then he saw the results of the experiments, he would have changed his mind because he has to. But yeah, they don't cohere. That's the point. I mean, I'm sorry, it was like Einstein was just wrong there. He's a smart guy, but he wasn't that smart.
But not everybody grants that point. I mean, I remember reading something by Sean Carroll where he argues or makes the point rather forcefully that it's just a misunderstanding to think that this implication contradicts relativity theory. Now, so I'm sure you're aware of the maneuvers that people employ to try and make them coherent. I mean, why are those mistaken? What is the
Sure,
misunderstanding?
that's easy
that
to
those...
say. It's because they do two things, both of which I think are wrong. The first one might not be wrong, and the second one certainly is wrong. The first thing they do is they say, okay, yes, I have a theory that violates Bell's inequality, but still you can't use it to signal. Now, I can't logically prove that that's not true. I doubt it. But then they make the second mistake, which is clearly wrong, which is to say the fundamental principle of relativity is about signaling. It absolutely isn't. Signaling is not even the right kind of thing to state a fundamental theory in terms of. I mean, this is like in quantum mechanics. In standard quantum mechanics, there are various principles that are stated in terms of measurement. And that leads to what's called the measurement problem. And Bell was very forceful in a paper called Against, quote, Measurement. He says the word measurement shouldn't show up in the foundational principles of any physical theory. It's just not the right kind of thing, right? It's like, I don't know, amusement or something, you know. Oh, a system will do something when it's amused. And you say, well, what the hell does that mean? You know, or you know, photons will do such and such when it's cloudy out. And you say, wait, cloudy isn't the right kind of word there. It's too vague. It's too unclear. You know, Newton didn't use words like that. Maxwell didn't use words like that. Signaling is like that too. What does signaling mean? How do you tell whether you can signal? How do you even define it? I mean, it shouldn't appear in the foundational statement of anything. It does not appear in the foundational statements of relativity. It just doesn't. The foundational principles of relativity are stated in terms of space-time geometry, not in terms of signaling. So I think that's, you know, you pile one mistake on the other. Anyone will agree, I think, if there's superluminal signaling, then relativity is out the window, right? I mean, that's just kind of straightforward. But my point is that it's not that if superluminal signaling is impossible, then relativity is in the window, because that's not this, right. You know, that's not the fundamental principle there. The fundamental principle is, can I write down my theory cleanly using only the space-time geometry that Einstein postulates and nothing more? And I think the answer to that is no. At least nobody's ever done it. And I don't see how you could do it.
Okay. Well, I can't refute you there. That seems pretty good. Okay. I'll have to hopefully goad Sean Carroll into coming on the podcast and poke at him about it. So I think that entanglement serves as an entry point into understanding quantum mechanics, or beginning to understand it. There's a distinction often drawn between the mathematical framework of quantum theory and then our physical interpretation of it. So issues that arise in the so-called foundations of quantum mechanics. What does it really mean in the end? And there are several different interpretations of quantum mechanics, but I wanted to ask you if you could briefly just touch upon, in a way that's roughly understandable to a layman like myself, the differences between, for instance, the Copenhagen interpretation and the many worlds interpretation, or Bohmian mechanics. Where do these interpretations differ? They all seem to agree, and this might not even be true, on the mathematical core, but they present radically different pictures of reality. So in a nutshell, what's that all about?
Okay, good. So that's a good question. The first thing, if you want to understand what's going on, is to stop using the word interpretation, because it's wildly misleading. The thing that they say you have that needs interpretation isn't a theory. It's a predictive formalism, right? So that you sort of start with a bunch of mathematics and some rules about how to use that mathematics to make predictions. If you start asking questions in a physics class, yeah, but what's really going on, right? What is this theory postulating about the physical universe? 9 times out of 10, you'll be answered with the famous phrase, shut up and calculate, right? I'm giving you the math. You know how to make predictions. That's all I'm going to give you. These other questions are bad. Go away. Okay. That's a really, really, really terrible thing to say. Why? Because very simply, most people who go into physics are not interested in making predictions, right? I mean, they're interested in finding out about the world. They're interested in trying to understand things. And so if I sign up for a course because I think it'll give me some insight, or at least possible insight into the physical world, and then you tell me, nope, I'm just going to give you a little predictive algorithm that you turn the crank on and spit out predictions, then I want my money back, okay? I mean, that wasn't what I signed up for. So what you really have are different theories. They're not different interpretations, they're different theories. They're very different theories. They're wildly different theories. In most circumstances, but not all, they make the same predictions. Now, because of that, it's hard to straightforwardly decide between them by going into a lab and doing an experiment, because their predictions are so similar. Certainly, if the predictions are exactly the same, then if you're going to make a decision, it's not going to be on the basis of that. So then you're, okay, what's going on here? Now I can give you a nice quick triage of your options. So at the very center of this mathematical predictive formalism is this thing that's called the wave function. And the wave function just mathematically is this non-local thing. It is not the values of the wave function, or the structure of the wave function isn't tied down to particular regions of space and time. Unlike, say, an electric field or a magnetic field, right? So in classical electromagnetic theory, I could literally point my finger and say, okay, what's the value of the electric field here, right? What's the value of the magnetic field here? Those are local things, what John Bell called local beables. The wave function, the mathematical object, has an amplitude and a phase, but you can't point your finger and say, what's the amplitude here? What's the phase here? It just doesn't work like that. It's a global object. It sort of describes the entire universe altogether. That's where this entanglement comes from. Now that's just about the math. Now the question is, what's your attitude toward that math? And here you have two choices. You either say, look, I think this funny non-local mathematical thing describes a real physical non-local thing, okay? I call that the quantum state, just to make the mathematical part and the physical part clearly distinct. I call that the quantum state. So you say, does the wave function describe, one way or another, this physical quantum state? If you say yes, then automatically you have something that never appears in classical physics, because this quantum state is not a local thing, and everything classical is local. So we're sort of done with that. Now, if you say no, this wave function doesn't describe anything physical, and the quantum Bayesians try to say this, then you're in a complete mess, because that's the central object in the theory mathematically. So what the heck are you doing, right? I mean, quantum Bayesians like to say psi, you talk about the wave function psi, you shouldn't attach psi to an object, you should stick it on your forehead, because psi doesn't describe the object, it describes your knowledge of the object, or your beliefs about the object, or God knows what. Whatever it is, apparently before there were human beings, there were no psis, because there were no people having beliefs about anything. This just strikes me as completely unacceptable and, absolutely hopeless. So I'm just going to leave that aside. We're now going to look at theories that accept that there's a quantum state, theories that accept that the wave function describes something physical.
Okay.
All right, now we have two choices. One choice is, now you can ask several things about it. First of all, you can ask, well, how does it behave? How does this thing evolve in time? Now, sitting at the center of quantum mechanics is an equation called Schrodinger's equation. And it's a deterministic equation. It's well-defined. It operates on these wave functions, and it tells you how they evolve in time in a deterministic way. You plug in the wave function at one time and a thing called a Hamiltonian, and it spits out the wave function at any later time. So, question. Does that equation always actually describe what it does? If so, then you have what's called a non-collapse theory. That just means the evolution is always this Schrodinger evolution. If you say, no, sometimes it does something else. Sometimes it does something very different called collapsing or reducing, which is a very different kind of behavior, then you have a collapse theory. So question one, is your theory a collapse theory or a non-collapse theory? If it's a non-collapse theory, you kind of have Schrodinger's equation. You say, here's what the wave function does. If it's a collapse theory, then you immediately have an obligation to try and explain when it collapses and how that goes, right? And there are different theories of that sort. There's a famous one associated with Girardi, Ramini, and Weber called the GRW theory. There's a theory associated with Phil Pearl called a continuous reduction theory. There's an idea for a theory by Roger Penrose that he called objective reduction theory. There were earlier theories in the direction that Penrose was going by a guy named Karoly-Hazy that tied collapses to gravity. So you have a spectrum of collapse theories. As soon as you have a collapse theory, you have this problem. All right, tell me about the collapses. Okay, this is physics. You can't just wave your hands, right? You got to give me some equations.
And wouldn't the Copenhagen interpretation be like the most prominent example of a collapse theory?
Let me get to the Copenhagen interpretation at the end, okay?
Sure.
So that's one question. Is it a collapse theory? Is it a non-collapse theory? The second question you want to ask is kind of the same question that Einstein, Podolsky, and Rosen asked, because the title of their paper was, is quantum mechanical description of reality complete? And by quantum mechanical description, they meant the wave function. Is that a complete description of the system? Once we admit that the wave function describes something real, this quantum state, it's certainly a partial description of your system. But it doesn't have to be complete. It doesn't have to describe everything. And in fact, the whole force of the EPR paper was to argue that it's not complete, that you need more than that. So that's, again, a yes-no question. If you say yes, there's something more than the wave function. And remember, this wave function isn't a local thing at all. So if you only have the wave function, you don't have anything local going on in space and time, which is a little weird, right? Anyway, so if you say, no, it's not complete, there's something else. And in fact, something else local, something that can be associated with individual places in space and time, what Bell called local beables. Then your question is, well, what are they? What are these local things? And there are various answers have been proposed. The most obvious one is that, they're particles. This is associated with Bohmian mechanics, what's usually called Bohmian mechanics, the pilot wave theory or the de Broglie-Bohm theory. You say, in addition to the quantum state, there are particles. What do you mean particles? Particles like Newton had particles like Democritus had particles, maybe point particles, tiny little particles that move around, okay? They're actually always located somewhere and they move. And the way they move is given by an equation that depends on the wave function. So there's something called the guidance equation. And the guidance equation determines how these little local things move. And then in that theory, you make up dogs and cats and chairs and so on out of these particles in more or less the way you always thought they were made out of particles. And you have the quantum state, and the quantum state determines how the particles move, and that's the end of the story. Then it's all analysis. The whole theory comes down to two equations: Schrodinger's equation for the wave function, guidance equation for the particles. Then the rest is analysis. If someone says the wave function's not complete and there's something else, then your first question, just as for the collapse theory, your first question is, well, tell me about the collapses. Your first question should be, well, tell me about these extra things. The Bohmians will say they're particles. Now, they don't have to. They could say they're fields. You can do a kind of pilot wave theory where the local stuff is fields. You can do a theory where the local stuff is, strangely, these things called flashes, which are point-like in space and time. So they're like little light bulbs going off. They're just little dots. That's the so-called flash ontology. That's fine. That's an answer. Tell me about it. Tell me how it works. Now we can actually triage everything. All right, so let me do it for you. Option one, the wave function collapses, and I want some of this local stuff as well. Then you tell me about the local stuff. So I said this collapse ontology, this collapse idea, one way it was clearly articulated mathematically was by Girardi, Ramini, and Weber. So they have this funny collapsy dynamics for the wave function. And then they add to that theory some local stuff and different ones. So there's a theory called GRWF, which adds these little local flashes. There's a theory called GRWM, where the M is a matter density in space. So you have this kind of more field-like thing. Okay, those are theories. That's one class of theories, a collapse theory with some local beables. Then you have a non-collapse theory with some local beables. That's Bohmian mechanics, pilot wave theory. They do kind of the same thing, but don't collapse the wave function, so they're okay with just having Schrodinger's equation. And then you have people who don't want to do either. They say, I want to keep the Schrodinger evolution, and I don't want to add anything. I want to keep the wave function complete, and I don't want it to collapse. And if you try and hang on to both of those things together, you're forced into the so-called many worlds theory. And you just don't have a choice about it. You're forced into it. This is a theory that Schrodinger thought was idiotic. That was what his cat example was supposed to show. He said, look, if you try to do that, then at the end of this experiment I'm going to describe, you're going to have to say the cat is neither alive or dead. And that's, he says, that's ridiculous. Of course the cat's alive or dead. What are you talking about? And you can think of the many worlds people as just saying, haha, hold my beer, Schrodinger. I'm going to run with this thing. And I'm going to say, no, I started out with one cat and I ended up with infinitely many cats. And you don't notice them because there are infinitely many yous and all this stuff. Now, personally, I think that's just such a conceptual mess and so hard to make any sense of that I'm not that interested anymore in even spending time on it. A lot of work went into it, and you sort of see why, because if you could pull it off, then the rest of your life would be easier, right? If you could pull it off, you say, well, all I've got is the quantum state. All it ever does is evolve by this equation, and I don't have anything else, and that's it. That's the end of the story, right? So I'm done. I don't have any local beables. The only problem is I don't have anything in space and time. I don't have anything I can interpret as dogs and cats. I don't have anything, I don't have a low-dimensional space-time at all. This is the kind of thing that Sean's trying to argue for, but good luck. I mean, I've thought about it for a long time, and I can't make any sense of it, to tell you the truth. So I would say, this is the first triage you want to do. Somebody hands you a theory. You say, good. Do you have a quantum state? If they say no, then God knows what they're doing. They're not doing anything even vaguely related to quantum theory. If they do, you say, okay, does it collapse? If they say no, then all right, you know what it does. If they say yes, it does collapse, then you ask for some more information. Okay, how does it collapse and so on? And then you ask, do you have anything in any local beables, anything beyond the quantum state? And if they say yes, then you ask about that. And if they say no, then you say, how in the world does this have to do, what does this have to do with the world I live in? Right? You haven't postulated anything that exists in space and time. Right? Whatever you're doing, it's not physics. That's what I think the situation is. Now, what about the Copenhagen interpretation? Well, the Copenhagen interpretation is not a clear theory. It's kind of a set of slogans. And the slogans go in all different directions. So on the one hand, Bohr insisted that the experimental apparatus must be described in classical terms. And since classical physics is all local physics, as we just said, electromagnetic fields, particles, things like that are perfectly local. If you have to describe the apparatus in those terms, you better have some local beables, right? You have to have some local stuff because that's how you're describing the experiment. So it seems like the Copenhagen people can't think the quantum state is complete. How does it evolve? Well, the kind of story is it's a collapsy story. But if you ask now for details, but when does it collapse? Then they say, oh, when you make a measurement or when you make an observation. And that's the point. Einstein went nuts. He said, what do you mean? I mean, he said, can a mouse do it? Right? You're telling me you've got this quantum state and it's evolving in this nice linear deterministic Schrodinger way until somebody looks, and then, you know, I mean, Einstein used to say, so you're telling me when I'm not in my bedroom, my bed is kind of slowly diffusing out, because that's what the wave function will do, right? My bed is slowly diffusing out, and as soon as I open the door and poke my head in, it snaps back into some place. And he says, that's crazy. I mean, it's crazy from every point of view, as well as, you know, who gets to collapse the wave function? And Bell made the same complaints. I mean, it's just a ridiculous theory. Why? Because it has the term measurement sitting in its fundamental principles, and that's bad. That's Bell's point. So Copenhagen just isn't something you can analyze, because it's just a bunch of words. I mean, they have this kind of predictive formalism, and then this kind of weird Bohrian philosophy word cloud around it that you can't make a whole lot of sense out of, and no clear equations and no clear account of what's going on at all. So pretty much the people I know who work on this stuff just leave that aside. They say, we can't work with that, right? I can work with the pilot wave theory. I can work with Bohmian mechanics. I can work with the GRW theory. I know what the many worlds people are doing, right? It's not that it's obscure what they're committed to. I don't quite understand how we get a recognizable physical world out of it, but okay, at least I know what they're doing. But Copenhagen is nothing that's at all clear or sharp or reducible to mathematics or anything. So pretty much people don't even try, right? I mean, why should I spend my time trying to make sense out of this mess when I have other theories that are at least well formulated that I can think about?
So is the Copenhagen interpretation not the dominant, or Copenhagen theory not the dominant quantum theory any longer?
Yeah, I would
seems to
say,
be the textbook.
Well, people say that. I mean, look, you have a whole generation of physicists who don't really have positions on any of this, because when they raised questions like this, they were all told, shut up and calculate. And shut up and calculate isn't any kind of theory, right? It doesn't answer any of these questions. It doesn't try to answer any of these questions. It just says, don't ask these questions. I mean, I can give you a bit of empirical feedback. Adam Becker, who has a background in physics, wrote a book called What is Real, which is a nice popular book for anybody who's interested in this. And he very strongly attacks Copenhagen in the book. And then he went and gave a lot of talks in front of physics audiences. And he was really worried that he would get very harsh treatment because of how nasty he was to Copenhagen. And he said it just didn't happen, right? He would go and criticize Copenhagen and the physicists would nod their heads. They don't understand it. I mean, they don't have the sense they understand what Bohr was saying. I mean, nobody who's read Bohr has a sense they understand what Bohr was saying. Bohr was rather proud of being Gnostic and incomprehensible, actually. So it's not like they're all big Copenhagen fans and you're in their face. They've more or less given up. Or if they even started. Why? Because it was never addressed in their physics classes. You know, these kinds of questions are not brought up in a physics class in quantum mechanics. They're not broached. It's not as if they say, oh, here are these problems and the right answer was given by Bohr. They just say, shut up and calculate.
Right. So the question almost doesn't come up.
Yeah. Question doesn't come up. Now, it's kind of a remarkable thing that physics could make such great progress as it did, certainly between 1926 and, the early 60s when the Standard Model was completed. It made tremendous progress without ever having to address these questions. And that's just a fact. But you might have the suspicion that at some point this is going to bite you, right? That this, shutting your eyes to the basic question, what's going on in the world? What is my theory really? What theory do I have here? That eventually you might get into some trouble because you refuse to even ask that question. And, maybe high energy physics is in the rather stagnant situation it's been for a while because of that. I don't know. But yeah, apparently, just as a matter of fact, you can go and insult Bohr in front of a audience of physicists nowadays, and they don't get upset. I mean, they're not big Bohr fans, but they're not really anything. They don't have any fixed views.
So just because I recently read Sean Carroll's book, Something Deeply Hidden, his popularization of the many worlds interpretation and a light defense of it, his main point, I think, in favor of the many worlds theory is that it's more theoretically virtuous than alternatives, primarily because it's simpler. He says repeatedly that it's the only quantum theory that takes the Schrodinger equation at face value and doesn't add anything to it in order to avoid many worlds. He says on several different occasions in the book that you can't avoid many worlds if you just follow the Schrodinger equation, and that everything else, every other additional mathematical frameworks, or the introduction of collapsing the wave function, that's just a means of avoiding many worlds because it's distasteful. It's subjectively weird. So I guess avoiding that excess, how would you respond to this? Like, is it theoretically simpler? And does that speak to its superiority to other approaches?
Okay, so let me start with something, because you made a claim that mixed together two entirely different things.
Okay.
Maybe this is, I don't really remember how Sean puts it. Maybe he puts it this way. Question one, do you take Schrodinger evolution seriously? Meaning, does the wave function always evolve by Schrodinger evolution? That's something you can mean. Certainly it's nice if it does, because then you write down an equation and there's the equation. Now, as I mentioned, the ones that don't are collapse theories. They say, no, we're not going to have it do that. We're going to have it do something else. And then they provide you with some equations. And yes, those equations are not surprisingly going to be at least a little bit more complicated, because the Schrodinger equation is actually a very simple equation. The pilot wave theory does not collapse the wave function. So in any sense, you can say it respects Schrodinger evolution just as much as many worlds. Then you have the second question, is the wave function everything? That's this question, is the wave function complete? And the pilot wave theory says, no, it's not complete. There's more to the world than the quantum state. There are particles, or there are fields, or there are flashes, there's something local. There's something that just exists in regular old four-dimensional space-time that we're familiar with in everyday life. And the many worlds people want to say, no, there is nothing. There is nothing. There is zero in addition to the quantum state. The quantum state does not exist in four-dimensional space-time. Now, you can ask the question, well, but isn't that a simpler theory? Well, sure, it's a simpler theory. It's an even simpler theory to say there's nothing at all. That beats them both on simplicity. But that doesn't explain anything, right? I mean, that's a simpler theory, but it's really crummy physics. So if you tell me I've got a really simple theory, the only drawback to it is there's nothing going on in space and time, I'm going to say, well, the simplicity does not outweigh the problem here, right?
Sure.
Because our empirical data is stated in terms of things happening in space and time, four-dimensional space and time, not infinite dimensional space and time, four-dimensional space and time. That's the thing that Bohr got right? Bohr said, we have to describe the experimental situation and outcome in those terms. And he's right, we do. That means you want something in your theory that corresponds to those terms. That means you want something local in a low-dimensional, four-dimensional space-time. And the many worlds people don't have it. They just don't have it. And then they do a big dance about how the fundamental space is infinite dimensional, but a small space-time emerges and stuff emerges, and you don't know what emerges
That's
means.
what I was going to ask about.
I have no, they don't know what they're talking about. To be honest, there is no clear theory of any of that. Nothing. There's just words. Emerges. What does that mean? How do I get a four-dimensional space-time to emerge from an infinite dimensional space? And why? And where does this emergence coming from? And where's all the, whereas if I say, you know what I've got in my theory? I've got a four-dimensional space-time, and I got some stuff in it. Okay, I got some particles in it. I got some fields in it. And I'm going to tell you how they behave. And it's true. When I tell you how they behave, I'm going to reference this other thing, this quantum state. That's a new thing, right? That's a real innovation. Prepare your mind for this. But the point of introducing it is to explain the behavior of the local stuff, because the experiments, setups, and outcomes are described in terms of the behavior of local stuff. So a theory with local beables in a regular kind of space-time is immediately interpretable as a physical theory that we can try to make sense of our experiments in terms of. And a theory that does not have that is a theory of something, and maybe a really simple theory of something. But it's not at all obvious how it even could be a theory of the world we live in. So I'm not, when Sean says people are trying to avoid many worlds, yeah, if that's many worlds, I want to avoid that. I really want to avoid that. That's not prejudice.
Well, I will tell you that when I've read like expositions of the many worlds interpretation, they make a point that like branches of the wave function, for instance, don't exist in regular space and time. Rather, they exist in this infinite dimensional Hilbert space.
Right.
And then they don't offer any further explanation of what that means, because my understanding is that the Hilbert space is a mathematical construct. It's not like literally infinite dimensions of space like we inhabit.
Well, yeah,
and so how could you have a branch in this mathematical structure? It just seems like a category error.
Yeah, I think you're absolutely right. And there's even a deeper error. People talk about Hilbert space as if it's a name of a single thing. Even mathematically, it isn't the name of a single thing. It's a kind of mathematical space. Hilbert space is a vector space with an inner product and a certain completeness in terms of limits being defined. And there are lots of different Hilbert spaces, and you define them mathematically. Now, sure, mathematically, I have no problem with the definition of an infinite dimensional Hilbert space, but God knows the world around me does not present itself as in an infinite dimensional any space, right? It presents itself to me as in pretty much a three-dimensional space. So, you immediately have this problem. Like what? Yes, you've defined something that exists in a very, very high dimensional space and is behaving in some pretty simple way. How do I connect that at all to the physical world I think I'm living in? And without cheating, I don't see how you do it.
It would be very hard to explain the emergence of space-time without relying upon spatial or temporal vocabulary.
Yeah.
Without
people talk about emergence and they'll say, oh, space-time emerges from some non-spatio-temporal structure. And I just could never understand what they were even proposing, right? It just seems to me the word emergence is this vague word that they're using to smear over a huge conceptual problem. I know what it means to say, if you individual atoms, put it this way, individual molecules cannot be liquid, okay? They're just not the right kinds of things. And a single molecule, it's not the right kind of thing to be liquid. And then you say, yeah, but if you put a bunch of them together, then kind of liquid-like behavior emerges from the collective behavior of all these molecules. That I understand, right? And you can make clear sense of that. But how a low-dimensional space with localized objects in it is supposed to emerge from an infinite dimensional space with, certainly nothing local in three-dimensional space in it.
Same. So, all right, I think that's good. We've talked about quantum mechanics, but let me pick your brain a bit about the other half, the other pillar of modern physics, Einstein's theories of special and general relativity.
Yeah.
Many scientists and physicists and popularizers of science will claim that those theories refute our common sense notions of space and time, and particularly of time. And I've always been skeptical of that, not just on my own authority, but reading other philosophers of science and physics who don't go along with that narrative. Now, it's my understanding that you as well would reject that implication that these theories refute everything about our common sense ideas of the passage of time and space and time as a four-dimensional block and so on. So what is usually taken to be the reason that these theories refute common sense theories of time, and then why is it that those implications aren't true?
Well, okay, so this is a little bit, again, different aspects of this question. At a detailed level, there's no doubt that the relativistic account of space and time is not the everyday intuitive account, because it lacks something the everyday intuitive account has, okay? And that thing it lacks is what's called absolute simultaneity. Newton was very clear that he believed in this, and he didn't think it was at all questionable at his time. And the way he put it was, an instant of duration exists at London and on the moon and in the farthest parts of the galaxy all together, right? So what did he mean? He meant a single moment of time, by which he meant an instant. You snap your fingers, okay? That's an instant of time. It's perfectly well defined to ask, what was going on the moon at that moment? What was going on Alpha Centauri at that moment? What was going on? Go as far as you like. That there is a global single instant of time spread through all the heavens, is what Newton says. And time is the succession of these instants, right? These instants come one after another in a certain order, and a certain amount of time passes between them. That's called duration. That's pretty much the everyday thought about time. And in relativity, that's not true. It just doesn't have that structure. Relativity postulates both special and general relativity, postulates space-time structures that do not have that. That thing nowadays is called a preferred foliation. So that's the word for it. Just track that word. Newton has a preferred foliation. Einstein gets rid of it. Okay? So if you say, is this special relativistic or general relativistic theory of space and time a departure from common sense? Yeah, it is. It sure is. How much of a departure at a practical level? Well, here's an easy way to think about it. So you take out this preferred foliation, you take out this absolute simultaneity in relativity, and you replace it with something that Newton didn't have, called a light cone structure. So in relativity, you use a certain kind of geometry that has built into it a light cone structure or a conformal structure. And anybody who's read a popularization has seen pictures of this in relativity, and it literally looks like a double cone, right? You open the book and there are these pictures of all these double cones. Every point has a double cone, a past light cone and a future light cone. Okay, so in your head, imagine this kind of double cone structure. And furthermore, in all those books, those cones are drawn so that the angle, the sides are going up at 45 degrees, right? So like that. Good. Now, in order to draw that cone in that shape, you adopt some kind of funny units, because you need time units and space units. And say the time units are seconds. Okay, that's okay. We like seconds. We all know what a second is. We know what a minute is. But in order to draw it that way, then your spatial units have to become light seconds or light minutes, which are really, really, really big in everyday scale, right? I mean, you're getting up to thousands of miles or, millions of miles, light years, hundreds of millions of miles. So if you drew that light cone using everyday units like seconds and meters or seconds and miles, they wouldn't look like this at 45 degrees, the cone would get flattened down almost to a pancake, right? I mean, the two lobes of it would never really come together, but the little gap between them is so thin that at everyday level you wouldn't notice it. So in that sense, for most everyday purposes, it wouldn't feel different to be in a relativistic space-time as in a classical space-time, right? It's true that it's theoretically different, but for everyday purposes, you would never notice. You only start to notice when you go to very, very, very big distances. And then you say things like, oh, if the sun were to suddenly blow up, you might think we'd feel that on Earth immediately. And then you'd say, no, you wouldn't feel it immediately. You'd have to wait 8.5 minutes, which is, how long it would take light to get from that explosion to us. Okay, and 8.5 minutes, that's a reasonable amount of time. But then again, the sun is very, 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 very far away. So, this is not everyday life. So yeah, it's certainly true that relativity suggests a space-time structure that's not intuitive. I wouldn't say it's intuitive. In terms of that space-time structure, you can then make a very clean definition of local causality. That's what Bell does. I even mentioned it. In a locally causal theory, this is a relativistic definition, all the causes of an event lie in or on its past light cone, and all of its effects lie in or on its future light cone. And you can have events that neither is inside the other's light cone. Those are called space-like separated. And classical physics doesn't have anything like that. This notion of space-like separation is a completely relativistic notion. Now, what Einstein did in 1905 was he built that theory, special relativity, but what he was building it for was to give a presentation of Maxwell's electromagnetic theory. And Maxwell's electromagnetic theory is a local theory in Bell's sense. In fact, in that theory, causes can't go faster than light, right? Electromagnetic radiation can't go faster than light. That is light. So that's a local theory. And then it took him 10 years, and eventually Einstein came up with general relativity. And what he did there was he was trying to account for Newtonian gravity, for gravity, for the kind of effects Newton accounted for. And he finally comes up with general relativity that is also a local theory in Bell's sense. And gravitational waves can't go faster than light. That's the fastest kind of influence you can have. And that can't go faster than light. So the two theories of relativity are perfectly fine for local physics. But what Bell showed is that the actual physics of the world isn't local. So sorry, I think Einstein, you're out of luck. I mean, I sympathize with Einstein. He was trying to do local physics, and he figured out a way to do it in a relativistic space-time. He didn't in a million years imagine anything like Bell's result. And once you have Bell's result, it's just very, very hard to figure out how to do that in the kind of space-time structure Einstein postulated. And in my opinion, what has to give there is Einstein. I think the right thing to do is give up on relativity, because it doesn't have the resources to do this non-locality in any clear way. And what you need to do it is this thing I called a preferred foliation, the thing that Newton had, this global slicing into these successive moments. That's what Einstein got rid of. But if you bring it back, now you can do non-locality quite easily, simply, mathematically. You make use of that. And that's the way I think it should go. Now you need to explain something. You need to explain, why did relativity work as well as it did?
That was going to be what I was going to ask.
That can be explained. I mean, we've done that over and over again. We replaced Maxwellian electrodynamics with quantum electrodynamics, which is an entirely different kind of theory. But then we look back and we say, oh, but I can explain why Maxwell worked as well as he did. We replaced Newton's dynamics with quantum dynamics, which is entirely different. but we look back and we say, oh, but I can explain why Newton worked as well as he did. We replace Newtonian gravity with general relativity, entirely different theory, but then we look back and we say, I can explain why it worked as well as it did. I think we go to a theory with a preferred foliation, and then from that standpoint, we can look back and say, well, here's why Einstein did as well as he did, from a very different basis. So that's what, I mean, it goes by the name, I gave it the name emergent relativity. But by emergent there, I don't mean anything weird. I just mean from this non-relativistic theory, explain why the relativistic theories made as good predictions as they made. That's, you know, and you have to do that because they made good predictions, right? Everybody's got to do that. Whenever you modify a theory, you have to somehow explain the success of the old theory, even though you're abandoning the old theory. So that's something we're familiar with.
I can't help but ask you a more technical question about the distinction that I've read from the work of William Lane Craig in this context, who is a much more prominent philosopher of religion, but also works in philosophy of time, or used to.
Yeah,
and in his book, you what?
I know, I'm familiar with.
I'm just saying for
with
the
William
audience.
Lane Craig myself, so okay.
Yeah. So in his book, Time and the Metaphysics of Relativity, he makes much of the distinction between an Einsteinian interpretation, a Minkowskian interpretation, and a neo-Lorentzian interpretation of special relativity. Is that a standard set of distinctions? And then how does what you called emergent relativity, which is very interesting, relate to that? Because to my ears, that sounds like neo-Lorentzian relativity, at least on the surface.
Yeah, I mean, look, special relativity is, in some sense, very central to it, or a set of transformations called the Lorentz transformations. And Lorentz came up with these transformations before 1905, right? I mean, this was before Einstein. It's not like he read Einstein and then came. It's the other way around. Lorentz came up with these transformations. These are coordinate transformations, just thinking about Maxwellian electrodynamics. And in Maxwell's theory, the way it's stated, it's in Newtonian space time. So you have this preferred absolute simultaneity, okay? And a normal set of coordinates would introduce a time coordinate where every event that happens at the same time gets assigned the same t value, right? Now, you know, we don't always do that. Actually, we don't do that because in different time zones, as it were, the same event gets assigned different t values. You know, you go over to a time zone and the very same event is now said, oh, it happened at 10 a.m. instead of 11 a.m. That's, you know, so you don't have to assign simultaneous, even if there are simultaneous events, you don't have to assign them the same t value. What Lorentz realized was that because of a certain symmetry in Maxwell's equations, Maxwell's laws, which held in this kind of special frame, special set of coordinates, those very same laws would hold in these funny coordinates, these kind of strange coordinates that he discovered, that Lorentz discovered. And in these strange coordinates, they have a t coordinate, what you'd call a time coordinate, but the events that take place at different times are all assigned the same t coordinate. So what Lorentz thought is, okay, these are kind of some weird, very artificial, non-natural coordinates, but they have this interesting feature that if I write down Maxwell's equations in terms of these coordinates, they take the same form as if I write them down in the normal coordinates. And for certain practical purposes, that turns out to be a very useful thing. It makes it easier to solve some equations. You transform to these new coordinate systems, and then some of the calculations go easier. So that was Lorentz's thought, right? Lorentz found these funny coordinates, and he didn't think much more about them, except those are interesting coordinates. Einstein in 1905 writes this paper. It's a little hard, really looking back on it, to understand exactly what was in Einstein's mind. I mean, it's the paper's all written in this coordinate-based math. It's it's a little hard to follow. Pretty soon afterwards, his teacher Minkowski, his math teacher, looks at what Einstein did, and then says, oh, you're really postulating a new space-time structure, which is why we call it Minkowski space-time and not Einstein space-time, because it was Minkowski who figured this out. And originally, Einstein was kind of resistant to it. He wasn't all that happy with what Minkowski was saying, but after a while, he came around, and everybody came around and said, okay, that's really what Einstein did, was he postulated a brand new space-time structure, very different than Newton's, and very different than the one that Maxwell was thinking of, and very different than the one Lorentz was thinking of. Now, the Lorentzian point of view, what people usually call the Lorentzian point of view, is the one I just said. It says, look, he never gives up on absolute simultaneity. He never gives up on these simultaneity slices. He says, no, they exist, and there's one special coordinate system of these many that I've written down that's special, because only in that coordinate do all these simultaneous events get the same t-value. Whereas in Minkowski space-time, there is no simultaneity, and none of the coordinate systems are different than any of the others. They're all equal. There's no special one. And that decision between those two ways of thinking about it was not resolved and could not be resolved empirically. You can't resolve it by doing an experiment, because all the predictions of the Lorentz way of thinking of it will be the same as the Minkowski way of thinking of it. Physicists tended to go with Minkowski, kind of Occam's razor-y thing. They said, well, you know, on Minkowski's view, I don't need this absolute simultaneity, so I'll get rid of it. But that was not forced on them by any observations. That was more like this thing that Sean is saying, oh, it's the simplest thing to do, let's do that. Now, my response at this point is, yeah, I understand, because at that time, you really didn't need that foliation for anything. What the Minkowski way of thinking about it did was to allow you to think about what was going on in a completely foliation-free way and make all the right predictions and everything. But once you get to Bell and once you get to quantum theory, man, I want that foliation back, because it's very hard to even understand it without it. So I think you ought to bring it back. Now, that doesn't mean going back to Newton. It just means going to some space-time structure with a preferred foliation. What I've been working on for some years is actually an even more radical thing. It's a completely discrete space-time. It's one that's not a continuum.
All right.
And it has built into it a preferred foliation. And again, from that, what I would like to get is for various things to emerge, and that you understand why, if you squint at it the right way, it sort of looks like Minkowski space-time. But that's work in progress.
So I think that that's a good explanation of how the loss of absolute simultaneity is a radical adjustment to our common sense notion of time. Sure. But that's usually only half of what scientists will claim is eradicated by relativity. The other half of the picture is Minkowski space-time, this wedding together of space and time into space-time. It seems like when you view these graphical representations of space-time as this four-dimensional structure, that seems to lend itself to this ontological claim about space and time of the four-dimensional block universe view, that there really is no difference between past, present, and future. All events in time are equally real, and the passage of time, temporal becoming, is an illusion. That's a prominently held theory of time. And then the claim is that relativity lends itself to that theory. So it's not just the loss of simultaneity, it's also this loss of a genuine distinction between past, present, and future. Do you think that's the case, or is it not?
I think that's nonsense.
Okay.
No, I think there's nothing to that. I think that's just ridiculous. I can explain why, but I just want to tell you up front. I think everything that you said, you are absolutely saying what a whole bunch of people will say.
Right.
I think if you
step back
and look at it, it's complete nonsense. All right.
Okay.
First of all, I mean, people say, oh, there's this four-dimensional block universe. You can write down Newtonian mechanics in a four-dimensional manifold. You usually do. 3 space and 1 time. It's 4 dimensions. Okay. So a Newtonian universe described as it is starting at the beginning and going to the end, that description will be a 4-dimensional description. Does that mean nothing happens for Newton? Does that mean time doesn't exist? Of course not. Why would you think that? I mean, it's just crazy. You don't get rid of time by making a 4-dimensional representation of it, right? That's just a representation. If you want to say, well, my mathematical thing isn't moving, well, what the heck? What were you expecting? As I say, it's not that the block, I mean, people use this word like the block is frozen or the block is static or something. They don't understand. No, the block is not in time. Time is in it. That's why it's 4-dimensional, because it has not only space but time, and things in it can move because they're in a thing that has a time structure. It has a temporal structure. Now, you know, in relativity, the spatiotemporal structure is different from Newton, but not in a way that gets rid of time, and not that in a way that gets rid of the direction of time, and not in a way that gets rid of the distinction between past and future. I mean, it's standard in relativity to talk about the past light cone and the future light cone. And that's because there's a difference between past and future. And it's standard to only explain things going on now by reference to the past. I mean, I like to, you know, here's a simple example. The Earth right now is somewhere in the orbit around the sun. And if someone were to come up to a relativist and say, explain to me why the Earth is right here right now, they could certainly say the following thing. You might be dissatisfied at some level, but what they're saying isn't crazy. They say, look, a year and a half ago, here's where the Earth was. And here's the mass of the sun, and here's the other planets, and here's the laws of gravity and general relativity. And you solve all that, and you see, given that the Earth is going to orbit, and then right now it's going to be here. Okay? Now, people would say, yeah, that's kind of an explanation. Here's something they would never do. They would never say, you know, in 2.5 years, the Earth is going to be over there. And if you start over there and then time reverse this calculation, that brings it back here. That explains why it's here now. You're going to say, what do you mean that explains why it's here now? That doesn't make any sense. You don't appeal to the future to explain the present. You appeal to the past to explain the present. And that's as true in relativity as anywhere else. So yes, all it is to say that the universe is 4-dimensional is pretty simple. To locate an event like that, I need 4 numbers. Latitude, a longitude, an altitude, and a time. 4 numbers, 4-dimensional. Did I just make time go away? No. Does time go away in relativity? No. It has a different structure. It's expressed by what's called the proper time along a trajectory, but the proper time is time. The block isn't static. I mean, it doesn't even make any sense. The block isn't in time. Things that are not in time can't be static. They can't move, but they can't be static either, because what static means is stays the same as time goes on, right? For me to be static, that takes some time, right? For me to be static, I have to freeze. And that freezing has to last a period of time. If it doesn't, then I didn't freeze. So something that itself is not in time and is not persisting through time can neither move nor can it be static. It can't be frozen either. Those are just the wrong concepts. So when they say the 4-dimensional thing is static, it's just gibberish.
So I did read that in an interview that you gave, and I think that's a good point. But I'm still not clear on your ontology of time, because I think that even the B theorist of time, the eternalist view of time, the proponent of that view, will agree with you that, like,
before you go on, can you tell me what you understand by that view? Just tell me what you think it says.
So I would contrast it with presentism. The presentism, they're not the only two options for one's ontology of time, but a presentist metaphysic would say that only presently existing things are real. And
So you don't think
past events
Socrates is real? Is Socrates a
I
fictional
think that he's
character?
real in the sense. No, I think he's real in the sense that he did exist, or rather, according
Okay,
to
so
this
that's
presentist
reality,
view.
right? That's the difference between reality
Right.
and fiction.
Right. So I think
Dinosaurs are real.
it will. You what?
Dinosaurs are real. They're not made up.
They're not made
There
up, but
aren't
they
any right
did.
now, but they're real.
Right, but they no longer exist.
Yes, they no longer exist, but they're
Okay.
real.
So, agreed. I mean, yeah, it depends on how you parse the terms, but you do agree though that there is a difference between a eternalist and a presentist metaphysic, or are you arguing that they're actually
The
just
only
a
sense I can make out
semantic
of
difference?
presentism is the claim that the only thing that exists is the present moment. I can't make any sense out of that.
Okay.
So yeah, that's different, but if that's the alternative, I don't know how anybody can hold it. Because again, you have this problem. Here is a fact: Socrates existed.
Yes.
You need, for that to be a fact, you have to have something that makes it true. What makes it true is nothing going on right now. What makes it true is stuff that went on in the past. But if you say, oh, there is no past, then you've got nothing that'll make that sentence true. And now all of a sudden we don't have Socrates anymore.
Right. So this would be like the grounding objection to a presentist theory of time, that if you say that the only things that are real are presently existing things, then how can there be facts about the past?
Right.
But I don't know. I mean, I think that the right response would be to say that facts about the past. So the fact that Socrates existed is made true by the fact that there once was the object Socrates, rather than the fact that there is a presently existing object Socrates.
What kind of a fact is the fact that there once was a presently existing Socrates, given that that fact is not, is that fact in the present?
The fact is, right, there once was
aspect of the present makes that true? What aspect, what metaphysical aspect of the present makes that true?
Well, I think it would be that what the presentists would have to say is they would have to disagree with this account of grounding, that all truths have to be grounded in objects that present or that obtain. And it just comes down to which you think is more intuitively plausible, that all facts have to be grounded in that way, or that past objects exist in the same way that present objects do. And I would say that the latter is less plausible.
In the same way present objects do. I mean,
right, in the tense.
As David Lewis once said, people in the Middle Ages who had cancer, they were in pain, and their pain was just as real, right? It's not fictive pain, it's real pain. They hurt as much as we do. Don't downgrade stuff that happened in the past because it happened in the past. It just is real. I mean, again, the first distinction is between real and fictional.
Yes.
The past is not fictional.
Right.
So it's real.
Well, okay. But your analysis would then suggest that there's no difference between presentism and eternalism.
What I said is I can't make any sense out of presentism.
I see. Okay.
Eternalism is trivial.
Okay.
Eternalism, again, people get worried. Just does the future exist? And you want to say, well, look, Quine introduced a technical use of the word is. He did this for this purpose. He says, I'm going to introduce a slightly unusual technical use of the word is, which means is, was, or will be. Okay? That's just what it means. So in that technical sense of the term, there are dinosaurs. Are there, manned colonies on Mars? We don't know, but there's a fact. Either there are or there aren't, which is just another way of saying either there will be or there won't be. Or as I say, the deep philosophical insight of Doris Day, que sera, sera, right? There was one past, there will be one future, there is one present, and all the facts that are facts about reality are determined what they are by that entire collection. They're all equally real. Now, some haven't happened yet. Some have, some are going to happen to the future of now. That doesn't make them any less real.
Right. Okay. I'll have to think about that. I'm not entirely committed on a theory of time, but I have presentist leanings, so I'll have to contemplate this.
Well,
I appreciate
you will admit, if you're a presentist, then you should be worried about relativity, because relativity takes away the thing we normally call the present,
Yes.
which is this preferred simultaneous
Yes.
slice. But
And
even
William
if
Lane
you
Craig
keep it,
is,
I mean,
right.
the stuff going on that slice right now, to me, is way, 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 way too thin to provide truth conditions for everything I think that has truth conditions, including Socrates' existence. I don't know that you could derive it from anything there. Now, you can put kind of ghosty facts on it. You know, the fact that Socrates once existed, I hereby denominate a thing that presently exists on this thin little slice. But what kind of a ghosty fact is that? I mean, I'm happy with facts about electrons and protons and stuff like that. What is this ghosty fact that Socrates once existed that is a presently existing thing on this instantaneous slice? I don't know. It's not physics anyway.
No, and I mean, it may relate to, as we close out, the final topic I wanted to ask you about, which is the relationship between philosophy and science. And we could ask more specifically between physics and metaphysics. One of the pushes in modern metaphysics, I think, is to reduce its significance, in that many philosophers don't think of metaphysics as a source of truth in its own right that could supplement physics. Rather, metaphysics' role is just to follow after science and to reflect upon scientific theories and work out its conceptual implications. But that metaphysics itself, philosophical reflection, can't really issue in substantive conclusions about the world independently of empirical investigation. I gather that your views are more along those lines, or am I mistaken?
My view is that people are making a huge mistake because they're assuming what the word metaphysics means is what Kant decided it ought to mean, and nobody else ever thought that before.
Okay.
I mean, you have to stop a minute when you say, but what about metaphysics? Again, just stop a moment and ask yourself, well, what do I mean by metaphysics? Now, the name, as you know, comes from a certain manuscript that Aristotle wrote. And
oops. Sorry, one sec. Oh, there we go.
Okay, the name metaphysics, ta metaphysica, was a name put on a manuscript that Aristotle wrote. The term metaphysics does not appear anywhere in that manuscript. If you asked Aristotle what's metaphysics, he would have no idea what you were talking about, right? A later editor stuck that name on the manuscript. So what was the topic there? Well, Aristotle calls it three things. In some places, he calls it first philosophy. That doesn't give you much of a clue, right? Except that he calls physics second philosophy. So it's physics adjoint, right? It's right next to physics in some sense. At some places, he calls it theology, but let's leave that aside. Then we'd get into the active mind and all this stuff. But then the one thing he calls it that's very clear, he calls it the theory of being, as we translate it, the theory of being qua being, or, you know, the qua is Latin, but the Greek term means the theory of things that exist simply insofar as they exist, right? What you want out of metaphysics, according to Aristotle, tell me what exists and essentially the kinds of existence there are. And he gives examples in his categories. He says, some things that exist are substances. They're these kinds of things. Some things that exist are quantities. Some are qualities. Some are actions. Some are passions. Now, he put pride of place to substance because he thought nothing else would exist if there weren't the substances. The substances play a special role. Metaphysics is just the analysis of what exists merely insofar as it exists. If you're a Platonist like me about mathematics, there's a metaphysics of mathematics, which is the question, well, what are mathematical objects? What kind of existence do they have? I happen to think they exist. They're not physical things. Of course, there are physical things, and if you want to know what kinds of things those are metaphysical questions. Are there wave functions? Are there quantum states? Are there particles? Are there fields? These are metaphysical questions. The claim that water is H2O is a metaphysical claim. Why? It's telling you what water is. What Locke called that was the real definition of something, as opposed to the nominal definition, right? There's a nominal definition that gets attached to a word like water, but you don't care about the nominal definition. You want the real definition. The real definition tells you, what is this thing? That is what physics is about. It's what chemistry is about. It's what biology is about. It's what cosmology is about. They're all doing metaphysics. So if you say metaphysics has nothing to add, I don't even know what you mean by metaphysics, right? It's not, metaphysics doesn't come after science. It's as it were part of science. Now, the problem is, like in quantum theory, exactly the questions the physicists are not asking are the metaphysical ones. What's really going on? What really exists? Are there really particles? Are there really quantum states? These are metaphysical questions. Now, how did we get away from that? We got away from it because of Kant. It was all Kant's fault. It was Kant who insisted that metaphysics had to be a priori, that it couldn't be empirical. Why did he do that? Because he made a mistake. His mistake was he first of all thought that true metaphysical claims had to be necessary. And then he thought everything necessary had to be a priori. And that mistake was finally fixed by Putnam and Kripke back in the 70s with examples like water is H2O, right? Water is H2O, Putnam and Kripke argued correctly, I think. If it's true, is necessarily true. It couldn't be false. You can't even cook up an imaginary world where water isn't H2O. But it's clearly not a priori. It's obviously empirical. It's obviously a posteriori in Kant's sense. So if there are a posteriori necessary truths, even if metaphysics has to be about necessary truths, it doesn't follow it's a priori. So the thought that you're expressing is people saying, well, what can metaphysics add if it's completely a priori? And I agree, the answer is nothing. But what the heck makes you think it has to be a priori? Kant's making you think that. Aristotle didn't think that. When Aristotle writes down his list of categories, of course they're empirical. Why does he think that there are qualities and quantities and so on? Because he looks around the world and he sees them. It was only Kant who thought, I have to derive the categories from pure thought or whatever. I mean, Kant was a weird guy. He had held some very strange views. But somehow people keep accepting Kant's definitions of things when we should have thrown them away a long time ago. And if you throw them away, then there's not a big problem. Metaphysics is the theory of things that exist simply insofar as they exist. That is, you're not interested in, you're not interested in details. It's a fact about existence, how many butterflies there are in Brazil or whatever. But that's not metaphysics, because it's not asking, what is the fundamental nature of a butterfly, right? What kind of existence does it have? Kinds of metaphysical theses. They're fields, they're particles, they're space-time. These are all metaphysical theses. Why? They're postulates about what really exists and what nature it has. So the distinction between metaphysics and science should never have been made. It was made by Kant, and then after he did that, the logical empiricists came down hard on metaphysics, right? I mean, you read Carnap, Elimination of Metaphysics Through Logical Analysis of Language. Who's he's attacking? He's attacking Heidegger, for God's sake. I mean, metaphysics got a bad name coming out of Kant and led to a lot of bad philosophy. And then the logical empiricists reacted against that. But once you sort through the whole thing, and once you take on board what Putnam and Kripke did, which already is there in Locke in a certain way, and certainly, again, Aristotle never says it's a priori. So, yeah, if you thought it had to be a priori, I could see you'd have a problem. But the solution to that is to give up the idea it's a priori.
I think that's a useful correction, but I think the question at the heart of that poorly phrased question is, do you think there's a place for a priori metaphysics today in any
No,
measure, or do you think it's
I don't.
all
Well,
bunk,
not much.
so to
I don't know.
speak?
Maybe math. Maybe philosophy of math. I said
Mm,
philosophy of math is a kind of metaphysics because you're asking, do mathematical objects exist, and if so, what kind of
okay,
existence they have? Probably that's not going to be informed by empirical research. Why would it be?
right,
Um, Moral values. I happen to think they're objective moral values, but I don't think my reasons for that are empirical. But
okay,
if you're doing physical, if you're asking about physical ontology, of course it's going to be informed by physics. Why wouldn't it be?
okay,
You want to know about space and time, you better take account of physics, right?
sure,
And
okay.
if you're going to talk about space and time, you better know about gravitational wave detectors. I mean, they're relevant. I mean,
Right. Okay. Yeah, I think then we're much more in agreement on that point than I thought we would be after I read these kind of uh, short snippets of your views on metaphysics. I think more or less we're on the same page about that.
good,
That it's gonna be very difficult to come up with true information about the physical world from the armchair, so to speak.
right? And look, I agree. A lot of metaphysics is done that way. I mean, all this analytic metaphysics about trope theory and this and that was hot when
Yes.
I was in graduate school. I don't have much time for that. I don't find that very useful. And why? Because it just doesn't hook up to science at all. And it
Yeah.
just looks like kind of idle speculation that hard to see what grounds you would have. But if you start asking about the nature of space and time, man, you can do more than idly speculate. And what you do better be informed by some empirical knowledge. How else are you going to find out about space and time? Insofar as you can, right? You do it empirically, of course. It's such a triviality to me that I don't understand why people think the way they do, except that they've been poisoned by Kant somehow.
Yeah, I think that's a fascinating take on the state of metaphysics today. Well, thank you so much for coming on the channel, Tim Maudlin. This was a fascinating conversation, good pushback, and I really appreciate it.
Sure. Happy to be here.